Hello, hello, hello. Hello, hello, hello. Hello, hello, hello. Hello, everyone. Step right up, come right on in. It's time to learn some more electricity and magnetism. Yay. Honestly, electricity and magnetism is probably, other than relativity, it's my favorite part of physics. And in some ways, I like it more because it's so much less complicated than relativity, or at least than general relativity. I hope everybody had a wonderful weekend. Anybody have any questions while we're waiting for the rest of the people to get in? We're starting chapter 22 today. I did make some videos. I had some problems with posting them. Hopefully they'll be posted this evening. I have one from 113 that wasn't posted. I think it's not your class. I think that's a 241. Plus I made a couple videos on dipoles, electric dipoles, which your book covers. And I told you to make sure you knew them, but I wanted to do some actual derivations and make sense of it for you, and do some integral electric field calculations. So I did some of those over the weekend, and I just have to upload them to my YouTube channel. So again, you guys might want to subscribe. I'm not trying to make you. I'm just saying if you do, then while the semester is going on, every time I post something new, it'll send you an email and let you know the title of the new thing that I posted. You can tell whether that's a 241 or 242 thing that's been posted, and then you can go see it. And then when the semester's over, unsubscribe if you want. But of course, I obviously want more subscribers because, you know, I'm going to clearly get rich on my 8 people a semester that look at it. Actually, it's not monetized. I should let you know I have not monetized it. I can't, even if I wanted to, just because I don't have enough hours and views and all that good stuff.
Professor,
Yes.
I have a question about the homework.
Okay.
2161, it's about an integral, and it's relating it to the period, or finding the period.
Okay. I tell you what, I made it where you can share your screen. Are you looking at it right now?
I can pull up in a bit.
Yeah, you show us the screen and then we'll work on that from there.
Oh, I remember that one. It's yeah, it was like you had to use the simple harmonic motion formula or something.
Yeah.
That one.
Yeah, whenever you have an equation that's like a second order derivative of something with respect to time plus something times the first order derivative plus something times the zeroth derivative equals 0, then that automatically gives you a simple formula for one that's a harmonic oscillator, and then you just take the coefficients, and that actually makes your period, actually makes your frequency, and then you can do 1 over the frequency to get the period. But that might be what it's related to. If you once we pull it up, we'll see.
Professor, I pulled up the screen.
Okay, I see it. Gotcha. Yeah, this is nice. Yeah, I remember this problem. So we calculated, actually we didn't, but your textbook, I calculated this weekend. That's why I said we, because that was one of the things I did for you guys. But I think it's already up there too. Another version of it's already up on my YouTube channel. But in your book, they calculate the electric field at some distance above the center of a ring of charge. So they're expecting you to use that equation and say F equals, MA, which is Newton's second law. The total force acting on it will essentially just be the electric field times the charge. So you take the electric field, ideally you derive it because that's what you're supposed to be able to do in this course, is derive that electric field. But either way, just take the equation for that and multiply that by the charge Q. That'll give you the force, and that's the only force acting on it. That's equal to m d2x over dt squared. because that's Newton's second law. And then I'll show you how this works. So now that I've got this, I know what it is. It's a distance x away. Okay, so let me steal the screen back from you. So we have an electric field created due to this
Nothing's
thing
pulled
being
up
a
yet.
ring of charge. What's that? Oh yeah, I got to turn the document cam on. Doo-doo. Thanks for, yeah, always remind me, guys. That's very appreciated. Even though I act like a goober and say I did what was right or something stupid, but I'm just being funny when I say that. So I'm looking back at the examples in the book to pull up the actual electric field that was calculated. But basically what you'll see is it turns out to be like a 1/r force or electric field. The electric field turned out to be Qx over 4 pi epsilon naught. So the electric field turns out to be the total charge Q times X, the distance away, over 4 pi epsilon naught, and then times X squared plus R squared. And that's to the 3/2 power. Okay, so we have basically right above the center is this charge little q. So you're going to multiply little q times that to get the force. So F would be Q X over 4 pi epsilon naught X squared plus R squared to the 3/2. And that looks horrible. That looks like super, super scary, right? But if you look in your back cover of your textbook, there's something called the binomial expansion, which says 1 plus X. I'm going to copy it down real quick. This is something else that's a wonderful derivation for you to carry out on your own. But basically it says that 1 plus X to the n power is equal to 1, dang it, lost it already. 1 plus or minus, and this is actually plus or minus n times X, and then it's plus n times n minus 1 over 2 factorial X squared plus or minus n times n minus 1 times n minus 2 over 3 factorial times X cubed plus ... That's the binomial expansion. And the reason why that's useful here is notice the little X they have here is supposed to be very, very, very much smaller than R. Okay, so if you take this X squared plus R squared to the negative 3/2, and let's say you factor out the R squared. So we'll say this is R squared. When I factor that out, that's going to become R squared to the negative 3/2. So that's just R cubed, R to the negative 3, I should say, times X over R squared plus 1 to the negative 3/2, which can be rewritten as R to the negative 3 times 1 plus X over R squared to the negative 3/2. So now with your binomial expansion, you can say this is approximately equal to R to the negative 3, which remember R is the radius. So that's not going to matter to us. That's not how far away it is. But I have that in the front of it. And then this is just like X, the X over R squared. So this is going to become 1, and it was plus, so it'll be plus here. And then n is actually negative 3/2. And then X, of course, is the actual thing that is X over R to the square power. So that's going to be X over R squared. And then the next term will be plus ... In actuality, you're not going to need to go any further than that, because if X is much, much smaller than R, then X over R squared is very close to 0 compared to 1. So what that means is F is going to be approximately equal to QQX over 4 pi epsilon naught R cubed, which is really just some constant times X. So now what you have is Newton's second law says QQ over 4 pi epsilon naught R cubed X is equal to the mass of the particle times d2x over dt squared. So we end up getting m d2x over dt squared minus, well, actually you can call it plus if you want. This could be minus r plus. We're actually calling it being attractive, so it should have been minus on that side. So now it'll become plus here, and that'll be q over 4 pi epsilon naught R cubed X equals 0. That looks just like m d2x over dt squared plus kx is equal to 0, which is a harmonic oscillator. And we know that the angular frequency omega is equal to the square root of k over m. Wait a second, k is m over k. So basically what you're going to do is take this and be the frequency, the angular frequency would be m divided by all this junk. Go ahead and look at this. It'll be d2x over dt squared plus k over m x. Yeah, that's right. Okay, so watch out. I gotta check my units for that. That's why I'm taking the time to do this again. So yeah, the square root of k over m is what ultimately becomes the omega. So square root k, or excuse me, yeah, k over m is the omega. That's right. Okay, so now the period, first off, you get the frequency is given by omega equals 2 pi f. So that means f is equal to 2 pi, no, omega over 2 pi. So your actual omega is going to become basically the coefficient of this when you get rid of this m. So your omega will be the square root of q over 4 pi epsilon naught r cubed m. So your frequency would become that junk over 2 pi, and then your period would become the flip over of that, which would be 2 pi over that junk. Does that make sense? Who was it that asked? Was that you, Colby?
It was me.
Okay. Reese, gotcha. So do you understand how I got that or why that makes sense?
Yes.
And yeah, it's really easy to make this mistake. I was treating this as period. That's why I first wrote it as m over k, because I knew the seconds had to be on the top. Then I remember, duh, this is frequency. So the units of seconds has to be on the bottom. I know k is the spring constant, which is basically newtons per meter. And the Newton has the unit of seconds in the bottom. That's why I knew that this had to be k over m for omega. So yeah, that's the nature of physics is on the very last day of your physics class, you're still expected to know what you learned on the very first day of your physics class. So just be prepared for that. That's the nature of the beast. It continues. So when we covered 14 and 15 last semester, it's still going to come back to bite you this semester. All right. Anybody else have any other questions? All right. The big trick, though, is to realize this binomial expansion. You can do this all the time. And normally you don't need any more than this term, these two terms. And a lot of times, like just now, we didn't even need that term because that x over r squared is infinitesimal if the particle is really close to the center of the ring, but not at the center. So you would see what they're saying is, yeah, obviously, if you put a charged particle in there, it's going to be deflected through it, back, through it, back, through it, back, through it, back, through it, back. And it's asking you what the oscillation frequency would be. So it's kind of a neat little deal. Anybody else have any questions before I go on to chapter 22? So yeah, what I did decide was I'm jumping on to chapter 22 since I made those other videos and there's other ones online. We'll get plenty of time to see all this stuff. So there's chapter 22, and that's called Gauss's law. Now, Gauss's law is actually Gauss's law. It's not, a lot of people think that it's only true in certain cases, and that's not the case at all. In fact, it's called Gauss's law because it's essentially always true. But the thing is, the way we usually use it, it's only valuable using it that way in certain unique symmetries, okay? But to introduce that, we first need to talk about electric flux. And electric flux is given the symbol phi or phi. And I will give you the full explanation of it. It's the integral of E dotted with dA, a differential surface element, okay? In the simple cases where it's a uniform electric field, the flux becomes the electric field times A times the cosine of the angle between them, okay? What do we mean by that? Well, let's imagine an electric field that's uniform. That means it has the same strength, say 100 newtons per coulomb everywhere, and the same direction everywhere. And let's say it is actually impinging on a surface like this. And what we do is we recognize this surface as having an area A, but we represent that as a vector that is perpendicular to the surface. So it's actually perpendicular to that line, it's perpendicular to that line, and its magnitude is A, which might equal B times C. Okay. So what we're doing by taking the cosine, what we're doing is we're imagining the two vectors as if they're tail to tail. So here's the E vector, and here's the A vector, and its magnitude, of course, is just B times C. I don't know why I put absolute value bars around it. I just meant to put around the A. And by doing that, what you're finding is this is the angle theta when they're tail to tail. And if you take the cosine of E times A, you're basically only going to get the component of E that's parallel to A. So you're imagining E being broken up into, let me use some colors here to make sense of this. We're going to imagine E being broken up into a vector this way and a vector this way. Looks like my red pen is definitely dying. Well, maybe not. Okay. This is the component that is parallel to the surface. And this is the component that's perpendicular to the surface. And I mean the surface, not the vector. Okay. But it's also E parallel to the A vector. Okay, so we're really just trying to find the components of E that go cleanly through the window as opposed to the ones that are sort of deflected away. That's really what it does. Now, if you happen to have an electric field that varies all over the place, then you're going to have to break this up into little differential area elements. And that thing might not even be flat. It might be quite curved. So you'll have to make it really, really small and then take the little E that's acting at that point and then sum it all up. That's why I give you that whole integral symbol. But in most cases, it's just something simple like, let's say we have, this is the angle 60 degrees, and the area of this is equal to 40 square meters. And then we have an electric field that is equal to 100 newtons per coulomb, and that points perfectly horizontally. Then we can take the area vector, which, by the way, it's arbitrary whether the area vector points this way or that way. Later, I'm going to make that unarbitrary. So right now, I'm going to say, okay, well, this clearly has to be perpendicular to that. So there's my A vector. And the magnitude of the A vector is 40 meters squared. Since this is 60, and this is a right angle right here, then this angle right here must be 30. And that's an alternate interior angle from this one. So that angle is 30. So we see the actual angle between the E and the A is 30 degrees. So I'd say the the electric flux is 100 newtons per coulomb times 40 square meters times the cosine of 30 degrees. And if you remember your special triangles, square root of 3 is this guy, 1 is this guy, 60 degrees is this guy, 30 degrees is this guy, and this is just 2. So the cosine of 30 is root 3 over 2. So that equals 4,000 Newton meters squared per coulomb times the square root of 3 over 2, which, if I remember correctly, is 0.866. So 4,000 times, I'll go ahead and type in cosine 30. So that's 3.464 times 10 to the third Newton meter squared per coulomb. Okay, now obviously I only had like 2 sig figs here at best. So really I shouldn't be counting this digit or this digit. So that's what a flux is. And it doesn't seem to be that relevant to life in general. But the amazing thing is that Faraday and Maxwell, well, actually not Maxwell, it's more Faraday and Gauss and Poisson and all these people that were working on this at the time, Galvani, Ampere, all these people saw that that quantity was important. And that quantity ended up being part of Gauss's law. So your book gives you a few examples of how to calculate this flux. The main thing is to realize there's a dot product in it. So you've got to create an area vector that's representative of the area that you're doing, okay? And points perpendicular, either one direction or the other, perpendicular to the actual plane. And then E has to be made into a vector field. You take a dot product of those and integrate them. Now, that being said, most of the integrals are going to become really trivial. And I'm going to show you the details, but it's not going to matter that much, okay? So let's go ahead and show you some of the details of that. So let's imagine this scenario. Now that we have somewhat of a sense of a definition of what a flux is, what I can do is I can create a box and calculate the flux going through it. So let this be my x-axis, let this be my y-axis, and let this be my z-axis. Notice that is right-handed. Remember, right-handed requires x to be my index finger, y to be my middle finger, and z to be that thumb. Okay, so this matches with that. So it's right-handed. We know everything's good. What I'm going to do is I'm going to go up 2 meters here, and I'm going to go over 3 meters here. That should be exactly parallel to that. Sorry about that. I'm going to go 3 meters here, and then I'm going to go 4 meters here and make a box. Okay. That's the box that I'm going to use, and I'm going to calculate the flux through that. And I'm going to assume my electric field is E is equal to, let's say, 40.0 newtons per coulomb meter squared times y squared. And it points, in fact, in the, let's say it points in the k-hat direction. Okay. So what I want to calculate in this case is I'm going to calculate the flux over the closed box. So I want the flux, and since it's integrated over a closed box, I'm going to put a circle around that integral. That just means I'm going over a closed surface. And that also means that we're no longer in the arbitrary region. In other words, the dA vector has a very specific direction. It points perpendicular to the surface, but outside. So the dA for the top surface would have to point up. The dA for the bottom surface has to point down. The dA for the right surface has to point right. The dA for the left surface has to point left. The dA for the front surface points out or towards us, and the dA for the back surface points into the page. Okay, so I'm going to calculate this. To do so, I'm going to label the surfaces. This is going to be the front surface. That back there is going to be the back surface. This is going to be the right surface. That's going to be the left surface. Down here is going to be the down surface, and up here is going to be the up surface. I tried to draw it so you could see what each thing labels. I hope that makes sense to you guys. So first off, let's take the up surface. This electric field varies over y, right? I do not want this integrand, which is E, to vary very much over the differential area, or I'll have to do some kind of averaging process. So what I'm going to do is I'm going to take and make this my differential area element, because this has only a thickness dy. So for the up surface, I'm going to say dA is actually equal to, now notice the width of this is supposed to be 3 meters, so it's 3 meters dy, but it points in the k hat direction. And I know that the electric field on the up surface is going to be equal to basically that number 40.0 with units, which I'll just put like that in there, times y squared times k hat. Y is going to go from 0 to 4 meters. Okay. Now I take my bottom surface, which is another one that's easy, but I called it down because obviously I already used the B for back. So this dA is going to be the same thing, except it points down. So I'm going to say this dA is 3 more meters with a negative in front of it, dy k hat. That makes it point down. E down is again going to be 40.0 dot 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 times y squared k hat, and y is going to go from 0 to 4 meters. Now I can do my left face. My left face doesn't have y varying at all. So I really don't care what variable or what differential area element I choose to use is. So what I'm going to do is I'm just going to say, okay, let's make this a thickness dx. And I'm going to say the height, of course, is 2 meters. So dA vector is going to be 2 meters dx. And and that's going to point, of course, in the negative j hat direction. Everybody understand that? Now the electric field is going to be 0 because at this place on this whole plane y is 0, so it's just equal to 0 vector. And of course, what we know is x is going to go from 0 to 3 meters. Now I'll do the right face. dA is going to be positive. I'll use the same differential area element. It's going to be positive 2 meters dx j hat, because it's going to point that way instead of this way. E is actually going to be 40.0 4.0 times, in this case, the y is 4. So that'd be with some units times 16 in the k hat direction. And of course, the x is going to go from x equal 0 to 3 meters. And now I can do the front face.
Is it in the J direction? Or is it in the K? The electric field.
Yeah, the electric field's supposed to be in the K direction. I've had it pointing up from that original definition. So the electric field only points this way. And in fact, it's 0 right here, and it gets up to 40 times 16, which is 640 newtons per meter or newtons per coulomb here. Okay, the front face, I'm going to do the same thing as I did before. Now this front face actually has a y, so I'm going to have to do it like this, where the y is very small. So I'm going to say dA is actually equal to, the height in this case is 2 meters times dy, and that one's going to point, since it's the front, it's going to point out, it's going to point in the I hat direction. The electric field is going to be 40.0 with some units times y squared in the k hat direction. And of course, in this case, we're going to go from y equals 0 to 4 meters. And then the back face is going to be dA is equal to -2 meters dy I hat. The electric field of this one is going to be equal to 40.0 with some units times y squared times k hat. And again, the y is going to go from 0 to 4 meters. So the flux is going to be the integral over the up plus the integral over the down plus the integral over the left plus the integral over the right plus the integral over the front. Whoa, that was supposed to be an integral symbol, became an L. Okay, plus the integral over the back. Okay, you probably can see already that a lot of those are just going to become 0. So first off, the integral over the over the top surface is going to be a k hat dot a k hat. So that one's actually going to survive something. I'm going to get 3 times 40, and this is newtons per coulomb meter squared. So times 3, that'd be 120 newtons per coulomb per meter. So that would be integral 120 newtons per coulomb meter times y squared k hat dotted with dy k hat. In other words, I went ahead and took the other part of the dA, which was the 3 meters. I stuck the dy and the k there, but I went ahead and multiplied the 3 meters times the 40 and got 120. But of course, it's meters times newton per coulomb meter squared. So it ended up being 120 newton coulomb meters. So this part's actually not going to be 0, but I am going to integrate from y equals 0 to 4 meters. And in fact, this is just going to become 120 newtons per coulomb meter times 1/3 of 4 meters cubed. Right? The k hat dot k hat is just 1, because remember, dot products A dot B is just the magnitude of A times magnitude of B times the cosine of the angle between them. So A has a magnitude of 1 unit, no number, no unit whatsoever, just a numerical unit. B has the same thing, so it's 1 times 1 times cosine of 0, which is 1. So that's what happened to the dot product. And now I just have 4 times 4 is 16 times 4 again is 64. So now I have 64 times 120.
Did you you got to divide by 3 too, I think.
Oh, thank you. And then divided by 3, that makes it a lot easier actually. Is 2.56 times 10 to the 3rd equals 2.56 times 10 to the third Newton meter squared per Coulomb. Notice this is a meter cubed. That's going to cancel out with a meter down there and leave a meter squared. So I end up getting exactly the units I expect for my flux. So that's the top surface. Next, I'll do the bottom surface or down surface. That's going to be negative. Then we have 3 times 40 again. So that's 120 Newton. It was Newton per Coulomb meter squared. I multiplied it by meters, so it's newtons per Coulomb meter, just like I had before. Now it'll be y squared k hat dot dy k hat. And this is going to go from y equals 0 to 4.0 meters again. I think you can see this is exactly the same integral we had before, except the negatives occurring. So I get negative 2.56 times 10 to the third Newton meter squared per Coulomb. So those two vectors, or those two integrals, actually gave me 0 when combined. When I do the integral of the left, well, that ends up becoming integral. Now the electric field was just 0, and it's dotted with negative 2 meters dx j hat. So that's actually going to be 0. When I do the integral of the right, in this case, I actually have a constant electric field. That electric field is going to be 640 Newton per Coulomb meter. Actually, newtons, because I already did 4 meters squared, and this was newtons per Coulomb meter. So this should be, yeah, this should be Newton meter up top. Over coulombs. And that's going to be in the k hat direction. But it's going to be dotted with the positive 2 meters dx j hat. Well, k hat dot j hat is just 0, so I get 0 again. In other words, the electric field had no component that was parallel to j, so the integral is 0. The integral of the front surface is going to become the integral of the electric field, which is 40 times, of course, I'm going to go ahead and take my 2 meters. So this will be 80 Newton per Coulomb meters, y squared, k hat dotted with dy I hat. So I get 0 on that one again, because k hat dot I hat is 0. And then the integral for the back is going to equal, again, in this case, it'll still be, I think, 80 newtons per Coulomb meter, y squared k hat dotted with negative dy I hat. So again, I get 0 there because k hat dot I hat is 0. So in fact, the net flux is exactly 0. So that's the gory details of a surface integral. When you have something like this flux, which is technically a surface integral, you have to evaluate the electric field and the dA on each of the individual surfaces, and then evaluate the E dot dA and the ranges of integration, and then do them bit by bit if they're, some kind of non-continuous structure like this. The good news is your book and your homeworks might have a single problem working this like this, but you sort of see the pattern. If the electric field points in the k hat direction, then anything with a dA that is not in the k hat direction, those integrals are going to become 0. So you don't really have to go through all this work. I just wanted to show you the details of what the work required. The good news is, like I said, hey, I know that the electric field only points in the k hat direction. So really, I'm only going to get a flux contribution from the top surface, which I called up, and the bottom surface, which I called D for down. Okay, so I would have automatically said this integral, this integral, this integral from the back, and this integral from the are all 0, and I never would have took that time. But now that you know, we can use Gauss's law, and Gauss's law is quite simple. It just basically, they concluded that if you integrate the electric field over any surface, that turns out to be equal to the total charge enclosed in that surface divided by the constant epsilon 0. So Gauss's law is the closed integral of E dot dA. Notice since we're using closed, sorry, I need to write it up there. I think that's what Enrique was telling me. So the closed integral, since we have that closed integral, the direction of dA is no longer arbitrary. It has to point out, okay? But that turns out to be Q enclosed over epsilon naught. So what does that mean? Well, that means we've got a lot of easy problems we can solve now, okay? And they get more complicated with more complicated charge distributions. But let's take, for instance, this. Let's say I have a charge uniformly distributed. No, let's just say we have a total charge Q. Okay, it's spherical. It has a radius R, and let's say it's uniformly distributed. What I'd like to do is calculate E for R greater than R. So what I'm saying when I use this R is I'm thinking about those spherical coordinates that I mentioned in that module 0. A spherical coordinate just means instead of using X, Y, and Z, we're going to use the distance from the origin as little r. And then like if your point was right here, if you drop that down, this angle right here would be theta, and that angle right there would be phi. That's what spherical coordinates are. So what I'm saying is I'm only considering R greater than big R. When I do that, then I have to evaluate what the electric field is. Well, from what I learned about electric fields is they point radially away from charges. This is a spherical charge distribution. So I expect the electric field to always point radially outward. So I make a hypothesis. I hypothesize that the electric field as a function of R, theta, and phi, again, you don't really need to know this. It's just, I'm saying I could have put X, Y, and Z in here, but because I'm using spherical coordinates, I think it's only going to be equal to a function of R, and it's going to point in the radial direction outward. So I put an R hat. The R hat is just, you imagine any point in space, you connect that point in space with the origin, and then the R hat points in that direction outward. And it's 1 unit long, okay? So that should make sense to you. Since this is a spherical charge, you'd expect that this direction would not have an electric field any different from this direction or this direction up or down. So it should only depend on the distance away. So that's my hypothesis. So now I take the left-hand side of Gauss's law, which is a closed integral of E dot dA, and I realize that my dA is going to be equal to some differential area element pointing also in the R hat direction, because it has to be perpendicular to the surface, right? And the surface perpendicular to that is always a radial line. So now I just say this is going to be E of R hat, dotted with dA times R hat. Well, guess what? E of R for a given radius R is a constant. So I don't have to keep that in the integral any longer. I'm going to say now it's equal to E of R integral. Now with the dot product, that's what we call a linear operator. So that means I can put this dA out in front over here and then just do R hat dot R hat. But R hat dot R hat is just, anyone? Anybody know what R hat dot R hat would be? 1, exactly, because they're 1 unit long and they're parallel. So I end up getting just the integral of dA, which is, lo and behold, the surface area of a sphere. So I say it's E of R times 4 pi R squared for R greater than big R. So that's my left-hand side of Gauss's law. The right-hand side of Gauss's law is actually sometimes the harder part. In this case, is actually easy though. So the right-hand side is Q enclosed over epsilon naught. Well, what I imagined here was a spherical surface. That's what I integrated over. And that spherical surface was a concentric sphere of radius little r. And its radius, like I said, was little r. Okay. You can see the total charge enclosed is just that charge Q, right? So that's just big Q over epsilon naught. Now I say left-hand side equals right-hand side. And when I get that, I say E of R times 4 pi R squared is equal to Q over epsilon naught. I can solve that for E of R, and I see that E of R is equal to Q over 4 pi epsilon naught R squared. R, going back to my original hypothesis, the electric field vector is Q over 4 pi epsilon naught R squared R hat for R, excuse me, R bigger than big R. So I just calculated basically Coulomb's law. So you can see, using Gauss's law this way, I have to have certain symmetries to do what I'm doing, which is literally I'm solving for the integrand. I'm solving for the integrand in Gauss's law. That's a weird thing to do, but it's neat that we can do it. Anyone have any questions about that? Now let's try the rest of this, because the rest of it is actually, I said it was uniformly distributed. So let's try the part where we say, what about if R is less than big R? Okay, well, what we said was Q was uniformly distributed. Okay, what that means is if you take any volume element and basically, well, yeah, if you take any volume element and divide it by the charge in that element, you're going to get a constant, and that constant is going to be rho. Okay, so what I'm going to do now is I'm going to again draw my sphere of radius r, or my.
Isn't it charge over volume?
Oh yeah, thank you. Thanks for correcting that. I even paused for a second and still got it wrong. Yeah, dq over dv. Thank you for that. Okay, so what we're going to imagine is a Gaussian surface inside of that. So we're going to put a spherical Gaussian surface. And the reason why I'm using a spherical Gaussian surface is I recognize that the symmetry of the problem suggests that it's going to be spherically symmetric charge. Therefore, it's going to make a electric field just like from a point charge. In other words, the electric field is going to point radially outward. And for that reason, the electric field will always be a constant on the surface, and it will be, in fact, perpendicular to the surface. So when I use the closed integral of E dot dA is equal to Q enclosed over epsilon naught, the E dot dA is always going to be some constant, because I know that on the surface of a sphere, the electric field will be a constant. And then the dA is going to be, in fact, parallel to the E. So the dot product's just going to become multiplication, and everything works out nice. So in order to do that, though, I've got to actually figure out how much charge is enclosed inside. That's going to be the hard part. So the left-hand side is fairly trivial again. I again hypothesize that E is equal to E of R only and in the R hat direction, and dA is going to equal some dA R hat. So that the left-hand side becomes E of R hat dot dA R hat, which equals E of R times the integral of dA R hat dot R hat, which is just E of R times 4 pi R squared. Notice this is pretty much what happens every time. And there's only 3 symmetries we use. We use cylindrical, spherical, and planar. So the left-hand side's E of R times 4 pi R squared. The right-hand side is Q enclosed over epsilon naught. So let's talk about Q enclosed for a second. Q enclosed is going to be the integral of rho dV. That rho is actually a constant, though. Okay. So you could actually realize that Q is equal to basically rho times the volume, and the volume of the whole sphere is 4/3 pi R cubed. So we already know that rho is equal to Q over 4/3 pi R squared or R cubed. That's what rho is. Now, if I take a sphere of smaller r than big R, then I could compute this integral, but I think you can figure out what it's going to be. It's just going to be integral rho dV for R instead of little r is just going to be rho times 4/3 pi little r cubed. Right? So I can look at, that's going to be Q enclosed. So I can say Q enclosed without doing any calculus. And you could do the calculus here, okay? That's perfectly reasonable, but why bother, right? If this rho was a function of R, then you'd actually have to do the calculus. And that's a problem that I sometimes assign. So, you know, I might want to make up some where rho is equal to some constant times R or some constant times R squared. It's really only rudimentary integration. But in this case, I'm going to say it's equal to rho times 4/3 pi R squared. But I know rho is 3Q over 4 pi big R cubed. And then this is going to be times 4/3 pi little r cubed. So lo and behold, I see that this 4/3 cancels out with this pi cancels out with that, and all I get is Q times R cubed over big R cubed. So the right-hand side, excuse me, of Gauss's law, Q enclosed over epsilon naught, just turns out to be Q R cubed over epsilon naught R big R cubed. Left-hand side equals right-hand side, gives me E of R times 4 pi R squared is equal to Q over epsilon naught times R cubed over R cubed. Notice those all cancel out with that, and I'm just left with R. So I see that E of R is actually equal to Q over 4 pi epsilon naught R cubed times R. So E is equal to Q over 4 pi epsilon naught R cubed R in the R hat direction. If I make a plot of the electric field as a function of position, what I'd see is that I can't write E evidently, is that it would be linearly increasing up till I got to the radius R. So I get a straight line like this. And that value would be Q over 4 pi epsilon naught R squared, because notice that I have a big R here, and that would cancel out with the 3 down here, making just R2 in the bottom, R squared in the bottom. And this would fall off like 1 over R squared, in other words, very rapidly. So that's what the electric field everywhere is for this charge distribution. So E is equal to Q over 4 pi epsilon naught R cubed R hat for R less than or equal to big R. You can see they're continuous. That's why I put that equal there. R, it's Q over 4 pi epsilon naught R squared R hat for R greater than or equal to big R. So it's just a piecewise function. And we now know the electric field for that. Now I only got 5 minutes. Y'all remember that nasty integral I did last time? So that was another example. That nasty infinite line charge, that was a booger, wasn't it? So check this out. I'm going to take, it doesn't even have to be infinitesimal. It can be a cylindrical one, which we can attack later. As you'll see, as the semester goes, we're going to repeatedly use this Gauss's law. But it's going to go on for infinity this way and go on for infinity that way. I'm going to set up my coordinate system such that this is X, this is Y, and this is Z. And in fact, I'm going to use cylindrical coordinates, where cylindrical coordinates are a different R. It's R in the XY plane, and then it's theta, that same angle measured counterclockwise from the positive X axis, and Z. That's cylindrical coordinates, just because that gives me a bunch of symbols I can use without having to explain them. Okay, so since this is infinitely long, I suspect that the electric field will always point, you know, if I go on the y-axis, it's going to point to the positive y direction. If I go to the negative y-axis, it's going to point in the negative y direction. If I get on the positive x-axis, it's going to point in the positive x direction. And in the negative x-axis, it's going to point in the negative direction. That's sort of the definition of radially outward by cylindrical coordinates. So sometimes some books will use the lowercase rho for this in cylindrical coordinates. I just use the same R. Okay. So my hypothesis is going to be E of R theta Z is just going to be E of R in the R hat direction. And dA is just going to be dA in the R hat direction. Now, if you look at those videos on the coordinates, you'll see the dAs. This dA, for instance, would be R d theta. Okay. But what I mean by it is I'm going to create a Gaussian surface because I realize this is going to have cylindrical symmetry. I'm going to create a cylindrical surface that is concentric with this wire. Okay, it has a radius R, say, and in fact, this little dA that we're looking at right here would be basically this quantity right here is R d theta, and this quantity right here is dz, and then the dA points out that way, which happens to be the same direction as the electric field. It points radially outward. But by choosing it cylindrical and concentric with the wire, I know the electric field is going to be a constant on it. So the right-hand side of Gauss's law becomes the integral of E of R hat and the dA
is it the left side or the right side?
Excuse me, yeah.
We're doing.
Thank you. Left-hand side. Woo, where's my brain today? dA R hat. Okay. So guess what? This is going to become super, super easy. By the way, I have to call this a length L. Okay, because the radius is little r, but it has another dimension, which is L. So in this case, I'm just going to get E of R times the integral of dA R hat dot R hat, which again is just E of R times the area. Well, the area in this case for the actual soup can label is 2 pi R times L. But that's not a closed surface. I actually have to have that plus the integral over the top and the bottom. It's got to be a closed surface. This cylinder without a lid and without a bottom is not a closed surface. So technically what's going on there is there's a little dA right here. And that dA is equal to R d theta times dr, and it points in the k hat direction. And down here, the same sort of thing happens. And that's dA down here. But you can see these parts are going to equal 0 because they're really going to become integral over the top is equal to E of R hat dot dA, in this case, k hat. So that's just equal to 0. And the integral over the bottom is just E of R hat dot dA k hat. So this is like those sides that I told you would automatically be 0. And it's just going to be 0 because R hat dot k hat is 0.
So, Professor, what is 0 again? Because
I missed the last part. You want me to explain that again to you? The top and the bottom?
it's kind of, can you retouch again why is exactly 0? I guess it's because
the dot product forces you to compare the components of the electric field that are parallel to the dA vector. The electric field is always pointing parallel to the XY plane, and K is always pointing perpendicular to it. So they all automatically give you 0. It's like those sides around the rectangular box that I did. Okay. Now, the right-hand side is easy peasy. And times about up, it's Q enclosed over epsilon naught. Well, Q enclosed, we're just going to assume it has a charge per unit length lambda. So it's just lambda L over epsilon naught. So we end up getting E of R times 2 pi RL. Actually, capital L is what I should have used. I think I used it over here. Should use capital L. Sorry about that. So 2 pi RL is equal to lambda L over epsilon naught. So E turns out to be lambda over 2 pi epsilon naught times R in the R hat direction. That's exactly what we got when I did it with that god-awful integral last time. So where class is done, there's a planar example that your book's going to do, and you're going to see some other examples on my YouTube channel that you should check out. But you can ask me questions on this tomorrow, or excuse me, the next class time as well. But we're going to continue to use Gauss's law into the next chapters. But I've done enough really for this chapter again, just for you to see this. The only difference with Gauss's law for a flat surface, you take an infinitely large surface, you'd use the same shape. But in this case, the electric field points up above the plane and down below the plane. So only the top parts are going to exist. And this soup label part will be 0. So you'll see that when you look at the textbook or when you look at my other examples on YouTube. You guys are free to go. Those of you who had me for lab, which I think is all of you, I will see you at 1:30. And if anybody has any questions, I can continue for as long as you need. And I can even work the example of the infinite plane if you want.
Isn't lab on Thursday?
Oh yeah, yours is Thursday. Sorry about that. That's my 241 students. I forgot. I just had them. I might stop drinking. I don't know. It's just looked like that might be the problem. I don't know. Thanks for coming, everybody.
Are we done with this chapter, Professor?
Yeah, it's a really short chapter, and I don't mind it being that short because I'm going to continue to teach you this Gauss's law stuff through the remaining chapters, or at least through several.
So when is the test for chapters 21 and 22 going to be due?
It should be on I'm actually using the date that's on the syllabus.
Okay.
So I'm probably going to open the practice. Actually, no, the practice test's already been open, so you're ready for that anytime. I'll probably open the test this week.
All right. Thank you.
No problem. Yeah, check your syllabus for what due date that first online test is. That's what I'm going to do. Anybody have any questions?
Yeah, I do, Professor. I will wait for everybody else, and then I will keep you like for 5 more minutes.
No problem. No problem at all. Aaron, Enrique, Jesse, Jessica, Reese. Oh, Enrique I already talked to. Anybody else have questions? Otherwise, I'm going to let Enrique fire. Looks like they don't. Enrique, fire away. Sometimes they just want to sit around and learn whatever you're learning.
It won't be long, Professor. First, I would like to thank you for holding me there. I know I was busy last week. I missed a couple of things. So I'm back again. I will try to catch up a lot more now with this. I saw the text is the one that we use, the one that you have in the math lab right there, right?
Right.
So, and that one comes with the e-text, correct?
Yes.
Okay, perfect. And then what else? So I have, for some reason, I guess my notes are wrong. What time is the class supposed to start? Like 11 o'clock?
Yeah, this class starts at 11 and goes to 12:20. Or excuse me.
Right, got it.
Oh shoot, I left class out early.
That's fine. No worries. I mean, I was just making sure.
I thought I was pressed for time. That's crap. I let everybody out early. I'm going to finish it up on the video at least since I screwed up. Oh crap.
Okay,
You're exactly right. I just made it an hour class instead of an hour and 20. Dang.
Yeah, I just want to make sure that we have everything. So I guess people will hate me later on. And then what else? I have that one. And besides, I remember last semester you make us buy the. Are we doing the same way with the test, like by the code and make sure we have a camera or
right? With this class, you need to, if the semester goes on where we have to stay online, you will need a camera like you have now to take your midterm and final, or else you'll have to like find a testing center to do it. But if the class goes back to the classroom, then we won't have to have all that.
Are we planning to go back in class? I mean, I love you and I think you explained great. However, your camera is killing me. You know that, right?
Yeah. Actually, it's not the camera; it's my internet link. The good news is the videos, they come out pretty good because I'm saving them locally, so the videos will be fine, even though they look like crap on here.
I said that's the only thing, and then okay, so we're about to buy the booklet, the
e-text, or you can buy an old edition if you want. If you want a hard copy of a book to keep, the third edition is very cheap and it's not that different. So you could use that for one to physically hold and read, but you get the free new version with the mastering MyLab and mastering package that they have at the bookstore.
So that's the mastering package from the So I guess got it. Which is the easiest book to honestly to order? Because I think just to buy this, if I have to relearn this one myself, is a lot tougher than that it seems.
There's a book by, God, I'm trying to remember the guy's name. There's another lower level book. I can't remember his name. I'll try to remember it. That's a little easier to read. But to be honest with you, all of them are about the same. They say just about the same stuff. Dang it, I can't remember. It's not Tippler. There was a one that the guy wrote. It was he wrote it for taking it alongside with calculus instead of having finished calculus 1 already. That book goes a little slower. What I'd say would be helpful to you would be the Shalm's outlines and Physics for Dummies. Make sure it's for the calculus base, not the algebra base. Those types of books are probably your best resource, other than just look at my YouTube channel and look at Khan Academy and that kind of stuff.
All right, Professor. All right. So thank you very much.
Thanks, Enrique. Hey, let me know when you have an email so I can add it to my class email or try to get one at TCC.
I truly appreciate your text message. After that, I jump again. It actually helped me because my curriculum was messed up, so I had to reach to a counselor. I guess I'm closer to graduation than I thought, and honestly, I think you are the only one who's stopping me for graduation. So well,
that's not good. You'll get it this time, though. I'm feeling confident. But hey, man, check out the videos, even if you have to miss class. Instead, just because you don't want to waste so much time, just watch my videos and don't even attend class, because you'll never get the video disturbance and you'll still get what I would prefer you to be here, obviously, but I don't want you wasting
I'll
time.
be here,
If
I'll
you
be
can't
here.
see anything, then why not just watch it there and come and ask me questions during
Yeah,
class?
I can see the major things, but what we not, so you know, what we cannot see are the details. You know, and those are the killers. So
Yeah,
when
well,
write a
you know,
really
stop
tiny
me and
letter-
ask me so I can bring it up close to you. I don't mind doing that at all, and it should, you know, it'll slow me down, which is probably helpful to you guys. So by all means, ask me.
I will let you know this time. I'm not gonna quit this time like I did before. So
Yeah, don't be a
I need
wallflower,
your
man.
class. Okay. Bye,
Thanks,
Professor.
Enrique.
Thank you.
Have a good one,
Bye-bye.
buddy. All right, so it appears that I stopped class a little bit early. So let me go ahead and do the infinite plane. This one, by the way, notice I did it for an infinitesimal wire. I could do like I did with the sphere and say the charge is uniformly distributed throughout, and then make this a finite size radius of the wire. And when I do that, then I'd have to switch to a volume element instead of a lambda element. I would be a rho instead of a lambda for the charge per unit volume. And I could integrate throughout and all that good stuff. It turns out most of these things, especially when you start to talk about AC, the electric field and the charge stuff almost all goes out to the outside edges anyway. So the more realistic problems are the one where it's sort of inside, there's no net charge and all the charges on the surface. Not only that, when you do that, the charge being on the surface ends up giving you a discontinuity. In fact, the electric field would be a 0 all the way up here. If this was just Q distributed on the outer surface, the electric field would be 0, 0, 0, 0, 0, and then it would jump up to Q over 2 pi epsilon naught, basically, is what the electric field would be. And then it would fall off as actually, it wouldn't fall off at all for an infinite plane, but for this one, it'd fall off as 1 over r squared. So I'm going to go ahead and work a positive, or excuse me, I'm going to work an infinite plane of charge as a Gauss's law. And you'll have it on this video already since I accidentally stopped class at 12 instead of 12:20. So let me kill this page right now. And what we're going to imagine is an infinitely large plane. So, and I'm going to do it in a very specific way. I'm going to choose my coordinate system such that Z points up, such that Y is actually in the plane of the paper, and X is also in the plane, or excuse me, is the plane coming out of the page. So the X is the axis pointing out of the page. Z and Y are actually in the page. Okay. So what I'm going to imagine here is I'll have this coordinate axis going way back here and this coordinate axis going way back here. But what I'm going to have is a plate of charge that's uniformly distributed. And in fact, it goes on forever this way, this way, and this way, and this way. And it has a charge per unit area sigma. So sigma is dq over dA, which I'm sure Colby would have caught me on if I did wrong. So that's a good thing, right? So what I imagine with this infinitely large plane is this little point of charge right here, for instance, if I consider a point right above it, it's going to be compelled to go straight up. And if I think about, well, this particle right here is going to make it go that way, well, then I realize, well, a particle over here is going to do exactly the same thing. So that's going to cancel out the components in the Y direction. Similarly, if I think about a charge here, that's going to make it go in the negative X direction, but there will be another one back here that's going to make it go in the positive X direction. So by and all, what I realize is that the electric field for an infinite plane should really just be pointing in the positive or negative Z direction. If I'm above the plane, since this is a positive charge, the electric field should be pointing up. And if I'm below the plane, the electric field should be pointing down. So my hypothesis is, this is a new way I started doing it, just call it a hypothesis. My hypothesis is that the electric field is equal to positive E of Z K hat for Z greater than 0 and negative E of Z, and I'll put a star on it because I don't know that they're going to have the same magnitude, but I suspect they will just from symmetry, for Z less than 0. So the only difference is I expect them to have the exact same form in V just from the symmetry of it. It physically can't be any other thing. But just in case you don't believe me, I put a little star on there to say maybe that's a different formula It's not. Okay. The difference is that it's going to point down below the plane. It's going to point up above the plane. So now I'm going to use Gauss's law. The closed integral of E dot dA is equal to Q enclosed over epsilon naught. Remember, it always has to be a closed integral. That's why they put that circle there to remind you. In fact, I almost forgot it on the last result. So I had to go back and show you, hey guys, I did include the top of that. They call it a Gaussian pill bottle. It looks like a soup can to me. So I say the top of the soup can and the bottom of the soup can have to be included, as well as the label around the soup can. But I'm going to use exactly the same Gaussian surface, but it's going to give you exactly the opposite results that I had before. So here's my Gaussian surface. It's going to be a cylinder that pierces the plane. And in fact, has a part at the bottom as well. Now I'm going to have a top surface right here, and I'm going to have a bottom surface right here. And then I'm going to have this, which I keep calling the soup label. Okay. So the dA for the top is going to be just some dA k hat. And the dA for the bottom is just going to be some dA with a negative in front of it, k hat. Because it's got to point down, because the closed integral makes the direction of the dA vector no longer arbitrary. It always points away from the center of the container. So this one has to point down. It's always got to be perpendicular surface, so it has to be k here. And then the dA for the soup label, that has to point radially outward. So I'm going to say dA r hat. And technically speaking, the dA for the top and bottom might be of the same form like r d theta times dr. And again, using double integrals there. And then the dA for the soup label is going to be different as well. That's going to be r d theta times dz, for instance, if you're using double integrals. But the main thing is you have to know all the parts of it. So the right-hand side of Gauss's law is the closed integral of E dot dl. This time I'm going, or E dot dA. This time I'm going to be careful and make sure I show you all the parts. The parts are the integral over the soup label plus the integral over the top plus the integral over the bottom. Okay, so the integral over the soup label is going to be integral of E of z k hat dotted with dA r hat. Now r hat in cylindrical coordinates, remember r hat only is a function of x hat and y hat. So or I hat and j hat. So r cylindrical is just equal to blah 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 I hat plus blah 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 j hat. And actually you can derive those. You'll see them on my webpage, probably on my YouTube channel if you want to. I think I put them up there. If you didn't, just ask me. I will gladly calculate them for you. It's kind of fun, and I'll probably do it this semester anyways. So you see here, this becomes the integral of E of z. Z is actually going to vary all over the soup label, so it's not a constant anymore. And the dA obviously has the form, like I said, r d theta times dr in the k hat direction. But the main thing is the fact that you got k hat dot r hat. This is 0 because there's no component of the electric field that's actually perpendicular to the soup label. So this is just 0. So unlike the other one where the soup label gave you everything that was important, in this case, the top gives you everything that's important. So the closed integral of E dot dl just becomes, or E dot dA, you keep slipping in the Ampere's law here. It's 0 because I already had the soup label, plus the integral over the top, which is going to be E of z k hat dotted with dA k hat. Now on that top, since that's an xy, it's parallel to the xy plane, the z is a constant, so that's just going to be a constant. And then for the bottom, I'm going to get the integral of negative E of z k hat. In principle, like I said, you could put a star here because it might not be the same, but as I told you, symmetry forces it to be the same. Dot dA k hat. Okay, and what I mean by that, symmetry forces it to be, for instance, if you were hanging from the ceiling you would think the top is the bottom and I would think the bottom is the top, and vice versa. So us having equal coordinates or having equal capacity to make our coordinate system shows you that they have to be identical. Okay, all the coordinate systems are allowed. The big thing here is notice the E of Z has a negative in front of it, and the dA has a negative in front of it as well. So the negative and the negative just gives you a positive. So I ultimately get 2 times the exact same integral, which is actually equal to 2 times the E of Z. Let me make more space for that. 2 times E of Z, because the Z is a constant on the top and the bottom, the integral of dA, which just equals 2E of Z times, let's just call it A. Okay, where A is that surface area. Okay, now the left-hand side is Q enclosed over epsilon naught. Well, Q enclosed, since this is a constant, the sigma is a constant, that means the sigma is the charge for a given volume. Well, you multiply sigma times a given area and you get the actual total charge. So sigma A is in fact the charge enclosed. So I write sigma A, again, the same A that we use there, over epsilon naught. Now I say left-hand side equals right-hand side. And with that, I end up getting 2E of ZA is equal to sigma A over epsilon naught. Notice there is no Z in here. So in fact, it's not E of Z. E is a constant. So E turns out to be the piecewise function sigma over 2 epsilon naught K hat for Z greater than 0. And sigma negative over 2 epsilon naught K hat for Z less than 0. And in fact, if you plotted that, it would look kind of neat, but you'd see a discontinuity and you'd find exactly a nice fundamental fact about electricity and magnetism, even though this is a special case. If you put Z on this axis and E on this axis, what you get is this is sigma over 2 epsilon naught positive for Z greater than 0. And then this over here is negative sigma over 2 epsilon naught for Z less than 0. And in fact, this discontinuity is equal to sigma over epsilon naught. And that's a fundamental fact. It turns out that electric fields are only discontinuous as far as the component that's perpendicular to a surface. The component that's perpendicular to a surface of an electric field is only discontinuous if there is a surface charge. And that discontinuity has a magnitude of sigma over epsilon naught. Okay, so that's another neat thing. And that's actually an electrodynamic fact. Is the component of the electric field perpendicular to a surface is continuous unless there's a surface charge, in which case it's discontinuous by an amount sigma over epsilon naught. Otherwise, it's not discontinuous at all. The magnetic field, on the other hand, has no discontinuity for a component that is actually perpendicular to the electric field. We'll also learn later about the component of the electric field parallel to a surface, and that has no discontinuities, whereas the component of the magnetic field parallel to the surface does have a discontinuity, and that discontinuity is equal to the surface current density, well, related to the surface current density in mu0. All right, so that's the last sort of symmetry that we needed to cover with Gauss's law. So I'll leave it at that. We actually went still less than the hour and 20 minutes we're supposed to get, but I think that's plenty. I'll do some more later, and that way this video won't be so long. Have a good one, everybody.